All right, next topic, the atom. So what you should know here are the different subatomic particles, where they're found, what the charge is, and their relative size, meaning compared to each other. So first up, we have the protons. They're found inside the nucleus. We abbreviate them with a little p and a plus sign since they're positively charged. The neutrons are neutrally charged, not negative, neutral, meaning they don't have a charge. So if you look at the overall charge of the nucleus, it's going to be positive due to the presence of those protons. The neutrons don't cancel out the protons at all, so overall it's going to be positively charged inside the nucleus. Now in terms of size, we use AMUs, not grams, because if you're dealing with one tiny little atom or one tiny little proton, which is even smaller, then grams don't really work because it's such an unbelievably small number. So people studying the atom came up with this idea of an atomic mass unit, and it's just kind of an arbitrary unit that they created that can help us compare different protons, neutrons, and electrons to each other and the masses of different elements to each other. So protons and neutrons are each about the same. They're each 1 AMU. And if you look at electrons, those little tiny negatively charged electrons zipping around in that electron cloud, those are so unbelievably small. 1/2000th of an AMU. So 1/2000th the size of a proton. They're so unbelievably small that we don't even worry about their mass when we calculate the mass of an atom. So when you look at the mass, it's only going to be equal to protons and the neutrons. We ignore the little electrons. All right, now Dalton. You should be familiar with Dalton and his conclusions and his atomic theory. His idea, let's set the stage here, his idea of an atom was just a solid ball, basically a solid little sphere. He didn't know of any protons, neutrons, electrons, any subatomic particles. He just thought this is one solid little piece. And he did say that all matter is made up of these atoms, and that's true. But he also concluded that it's indivisible and indestructible, and that is not true. We do know about subatomic particles. Over time, people learned about that, but it wasn't common knowledge at Dalton's time. Now, number 2, atoms of the same element are identical. That is not entirely true, but if you think about it from a historical point of view, he never knew about protons and neutrons. He never knew about isotopes, so he concluded that they were identical. They're absolutely similar, but they're not identical. But atoms of different elements have different properties, and that is true. If you look at a nitrogen atom, it's going to be different than a helium atom, or than a gold atom, or than a magnesium, and so forth. Number 3, atoms combine in whole number ratios. That is absolutely true. If you look at a formula, you're always going to see whole numbers. You're never going to see H, 1.670, 2.35. That'll never occur. It's always going to be whole number ratios. And finally, he concluded that chem reactions occur when atoms are separated from each other, joined together, or rearranged. They can't be changed into atoms of another element in a chemical reaction. Now, that's partially true. Under normal circumstances, you can't change an atom of one element into another. But what he didn't know about is a branch of chemistry that we call nuclear chemistry. He didn't know about nuclear reactions. And in these extreme situations, we can change atoms of one element into another by messing around with the nucleus and causing a nuclear reaction. But like I said, that wasn't common knowledge back in his day. So he was on the right track. He proposed a lot of things, a lot of statements, made a lot of people think. And then obviously spurred a lot of research, which led to the development of the current modern-day model. Which brings us to this picture here. Now, here you see the little itty-bitty tiny nucleus, and then you see this big fuzzy electron cloud. Now, the nucleus is where the protons and neutrons are found, and this fuzzy electron cloud is where the electrons are found. Now, the question says, which part of the atom makes up the atom's volume? Clearly, the electron cloud makes up the bigger portion of the atom. And I gave my kids an example of the entire giant stadium with a little tiny marble on the 50-yard line. The whole giant stadium would represent the electron cloud, and that little tiny marble would represent the nucleus. Now, the artist drew the nucleus here way too big. It should have been a dot even smaller than these dots. But if you did that, you wouldn't have seen it, so he wouldn't have done his job showing you where the nucleus is. So he had to draw it kind of big. But the nucleus is unbelievably small compared to the size of the electron cloud. Now, this is the fuzzy electron cloud that we've been talking about, but we now know, based on electron configuration, that that fuzzy electron cloud is actually made up of specific regions where electrons hang out. For instance, we have in here, the 1s orbital. two electrons are in that region zipping around and creating their own little mini fuzzy electron cloud. Then we have the 2s orbital. So we have a little bit bigger sphere. Then, when that's filled up, we got the 1s filled and the 2s filled, then we've got three of these 2p's, these little figure 8 guys. When those guys are filled, then we move on to the 3s, and then we move on to the 3p, and then we move on to the 4s, and then we actually go to the 3d and so forth. So we're building this overall fuzzy electron cloud by using these orbitals and energy levels and so forth. So yeah, it looks kind of like a big mess, but we hopefully know now that it's made of very specific regions where certain numbers of electrons hang out. So you should have an idea. We'll get into this a little bit later in another part, but this is basically showing you that this fuzzy electron cloud is a lot more specific than what it just looks like on paper. All right, Rutherford. Rutherford's gold foil experiment is the way that we learned about the nucleus. So you should explain Rutherford's gold foil and what he learned. Now he shot alpha particles, little tiny particles that are radioactive. He shot them at a piece of gold foil. He expected them to go through, and he wanted to prove that, so he surrounded the piece of gold foil with a fluorescent screen. He expected this top picture here. He expected all the particles to go through. He didn't know that there was a little densely packed nucleus in the inside here. So he expected all those particles to go through and light up in the back here, and I'll show you an animation of this in a second. And what he found was that some of the particles, most of the particles I should say, went through, but very few of them hit the nucleus and bounced back, or approached the nucleus and then ricocheted off or veered off. So if you look at this image here, you see what happens due to the presence of the nuclei. Not all those arrows come through. A lot of them are affected by that. So let's watch an animation quickly now, and let's see this in action. Okay, so let's take a look at Rutherford's model here. Remember, this is the alpha particles, or these are the alpha particles being emitted out of this little lead box here. They're only able to travel one direction. They pass through the opening in the fluorescent screen. He expected them to go right through the piece of gold foil and light up the fluorescent screen in the back. But every once in a while, he noticed that the particles actually didn't hit their mark. They bounced off on some weird angles. You see that one over there, and that one over there. And the fluorescent screen was used so he could see the flashes of light where the particles actually hit. So he was able to detect this. And as a result, he concluded that there must be a nucleus, a little densely packed particle, positively charged nucleus in the inside of that atom that those particles are actually running into and hitting. And that's what was causing them to bounce off and to be deflected. So he ended up with some unexpected results that led to the discovery of the nucleus. So here you see the alpha particles coming in and a couple of them just hitting or coming near the positively charged nucleus, and because of the same charge, they get deflected. So they end up on some weird angles. So this is what led to the discovery of the positively charged, densely packed nucleus in the center of the atom. Okay, number 5 here says, what's the difference between isotopes of the same element and what subatomic particle is always the same in all isotopes of the same element? Now, first of all, you need to know what isotopes are. Isotopes are identical, same element. So, for instance, lithium, lithium, lithium. They're all the same element, but they have different number of neutrons. So neutrons are the big key here. Neutrons change, and therefore they change the mass of the atom. Protons are always the same in all isotopes of the same element. So lithium, in this case, always has 3 protons. So if you look at the picture, the blues are the protons. 1, 2, 3, 1, 2, 3, 1, 2, 3. What does change are the number of neutrons. This one's got 3 neutrons. 3 protons plus 3 neutrons for the first one. 3 protons and 3 neutrons equals 6 total. So that's going to be your mass number for that particular element. And we see the mass number written right there. Protons, mass number. This one, we've got 3 protons, atomic number 3, but then we've got 4 neutrons. So we've got a grand total of 7. So that's going to be 3 protons, 4 neutrons equals 7 for a mass. And this one's going to have 3 and 5 and 8 for a mass. So what's changing here are the number of neutrons and the mass number changes. But what never changes are the number of protons. That's locked in stone. If you change the number of protons, then you have a different element. Number 6, how can you mathematically determine the number of neutrons in an atom if you're given its atomic number? Well, if you're given the atomic number, then that means you know the number of protons. And if you're given the mass number, you can subtract. You know the grand total, and you know the number of protons. This is like saying if you know how many kids are in the classroom and you know how many girls there are, you can subtract and figure out the boys. So you subtract protons from the total, and you can get the neutrons. Subtract the girls from the total, and you can find out the boys. All right, let's complete this table. I think we're going to be able to see everything that we need to see. Okay, this is kind of like a puzzle. You have to know what things are equal to each other, and that'll help you solve this. So let's start off with the first one here. We know we have 8 electrons and 9 neutrons. Now, if you have 8 electrons, we're going to assume that these are all dealing with unhappy atoms, unless you're in the noble gas range. But these are 8 electrons and 8 protons, so those two things are equal. If you have 8 protons, then we can go up to the periodic table and figure out what element it is. And if you look up here, I guess we do have to shift down a little bit. If you look up here, element number 8 is oxygen. That's got 8 protons. So let's take a look back at our table, knowing that we have oxygen. So we can fill in oxygen. Then our atomic number is going to be 8, because atomic number is equal to protons. The mass number is protons and neutrons together, so 8 plus 9 is going to be 17. And then our nuclear symbol is going to be our symbol. The big number on top is going to be 17. The smaller number on the bottom is going to be your atomic number, so 17 over 8. The isotope name is going to be oxygen. You can either write out oxygen or just put the symbol. Oxygen dash, and this is going to be 17. Which oxygen is it? There are a bunch of different isotopes. Which one is it? It's 17. If you just put oxygen 8, that would be very redundant, because everybody knows that oxygen is atomic number 8. What people don't know is which specific isotope you're talking about, so that's the information you need to put when you write the isotope name, the mass number. All right, is it a metal, nonmetal, or metalloid? The right side of this stair step, see the stair step over here on the periodic table? Anything to the right of that are nonmetals, so this is a nonmetal. Anything to the left of that are metals, and anything touching it, pretty much with the exception of aluminum, are metalloids, or semi-metals. Same thing. Okay. All right, magnesium. Magnesium is over here, element number 12. So it's got 12 protons. Its atomic number is 12. If it's going to have 12 protons, it's going to have 12 electrons. Hopefully by now you know it's not happy with those 12 electrons. It actually wants to kick out 2 and go down to 10. But for this, we're just dealing with neutral atoms. Later on, we'll deal with ions. Atoms are all neutral, so if you have 12 protons, you got 12 electrons. The mass number is neutrons plus protons, so that's going to be 25. Then we look at the nuclear symbol, big number over the small number, 25 over 12, and then you write Mg next to it, Mg-25, and it's a metal. It's on the left side of the stair step. And finally, we got iron here. Now we have enough information in this nuclear symbol to complete the whole thing without even looking at the periodic table. First up, we know the symbol. We know it's iron. Next, we know 26 is the number of protons, because that's the atomic number. And we also know if you have 26 protons, you have 26 electrons. We know 56 is the mass number, and if we do 56 minus 26, 30 is our number of neutrons. So then we can just complete this last isotope name, Fe-56, and it is clearly a metal, because it's in the middle. It's actually a transition metal, any of these guys, in this D block here. These guys up here in the D block are transition metals. These guys down here are the inner transition metals. Okay, in the F block. But those guys are all metals because they're on the left side of the periodic table. Now, number 8, last one. It says calculate the average atomic mass for the 2 isotopes of chlorine. So we know that one chlorine's 35, got a mass of 35, the other one's got a mass of 37. Now, the 35 is really abundant. 3/4 of the time you're going to run into 35, or only 1/4 of the time you're going to run into the isotope chlorine 37. So we have to take that into consideration. It's not just a 50-50 split. If they were each around 50% of the time, then we would say what's in the middle between 35 and 37? Boom, 36, there's our average. This is not just doing the old school averages here. Now you have to take into consideration the percentages that they're abundant in. So what you're going to do is take the mass times the percentage. Make sure you move your decimal point over. 75.77 turns into 0.7577. And then this one turns into 0.2423. So you multiply them and you get your subtotal. When you do that, you get 26.52 and 8.97. Add them up, you get about 35.49. And then when you look at that, you can just round to the tenths place like we typically do, 35.5. That's AMU if you're dealing with one. If you're dealing with a mole of them, it could be 35.5 grams. Okay, so two isotopes, you can't just take the average smack in the middle. What you have to do is consider the percentages, so you multiply, get your subtotal, and add them up. All right, all done with this section.